Welcome back. In this lecture, we will cover flow measurement devices. Measuring the flow of a fluid is very important varied applications in all kinds of process industries, where the quantities of fluid flowing in and out and the rates at which they flow need to be monitored and controlled. Flow meters vary widely in their operating principles, accuracy, versatility, capacity, and in the disturbance they cause in the flow, essentially through the pressure drop. We discuss here the operating principles of some of the more common types of flow metering devices. We limit our considerations to measuring incompressible flows only. Of course, the simplest method of finding flow rate is to let the fluid or a liquid flow into a jar which is calibrated. We measure the amount of volume collected in a given amount of time as measured on a stopwatch, and from these we calculate the flow rate. This is a typical method you use in the undergraduate labs, but in industry which are automated, this would hardly be desirable. One of the basic principles of flow measurement is to create an obstruction in the flow. And as we create an obstruction in the flow, the velocity changes and the pressure changes accordingly. If we carefully design our apparatus, we can create a situation in which the Bernoulli equation can be applied, and then we can relate the flow rate to the change in pressure. So we need continuity equation and Bernoulli equation to develop the relations for the flow measurement. Another type of flow meter is what is called a turbine-type flow meter. In this, a rotary blade, a turbine, is located between two sets of stationary vanes. As the fluid flows, the turbine rotates. The rate of revolution of the turbine is related to the flow rate of the fluid. A revolution counter is attached that will measure it. One design of such a turbine flow meter is given here. Here, the central mandrel which holds a turbine. The mandrel is kept in place by a couple of retainers. A magnetic pickup picks up the rate at which the turbine is rotating. Another type of flow meter depends on what is called a pitot tube. It is very commonly used in aircraft applications. Here in this picture is shown a pitot tube attached underneath a wing of an aircraft. It works on the principle that can be explained in the following manner. Consider a central streamline. This streamline, as it reaches the end of the tube, the front end of the tube, it is brought to rest. The fluid flows past this, around this. Since the fluid here can be assumed to be incompressible if the speed is quite low, then we can apply the Bernoulli equation between point 1 and point 2. At point 1, the velocity v1 is the velocity that we need to measure, the velocity v. At point 2, the velocity is 0 because the fluid has come to rest. It is a stagnation point. If the pressure at point 2 is P2 and the pressure at point 1 is P1, then the Bernoulli equation simply gives you P2 by rho g is equal to V square by 2g plus P1 by rho g. And from this we get V is equal to under root twice delta P by rho, where delta P is the difference in pressure between point 2 and point 1. Very simple method of measurement. Very accurate and has wide applications. Pressure P2 is designated as the stagnation pressure and is represented by P0. Pressure P1 is designated as the static pressure and is represented as P in most of the applications. How do you use pitot tube in an airflow? If the air is flowing, we could have the pitot tube arranged so that the end of the tube is facing the airflow. We could attach a manometer. The second limb of the manometer is open to atmosphere. So the reading on the manometer would indicate the pressure difference between the stagnation point and the atmospheric pressure. If the static pressure in the tube is atmospheric pressure, then this difference of pressure that this manometer measures is directly the pressure difference delta P of the last formula. In another arrangement, we connect the other limb of the manometer to the wall of the duct. And here, the pressure difference measured by the manometer would be the pressure between this point and this point. If the pressure drop across this length of the duct is negligible, then this pressure here at this point can be treated as a static pressure P, and this is the stagnation pressure. So the difference of the two pressure would be read here as delta P. So we need two pressures to measure velocity. One is the stagnation pressure or the pitot pressure, and the other is the static pressure. The pitot pressure or the stagnation pressure is measured by the pitot tube. Same arrangement. Another arrangement in the aircraft. These tubes are pointing in the direction of the motion of the aircraft, that is, in the direction of the oncoming fluid. Another arrangement that is quite popular is what is known as a Pitot-static tube, in which we pick up both the pitot pressure as well as the static pressure. The arrangement consists of two coaxial tubes. The central tube is open at the front end here, so it picks up the stagnation pressure or the pitot pressure. On the outer sleeve, there are a number of holes which are called the static holes, and these pick up the static pressure at that location. And this outer sleeve communicates to this pickup point, and the inner tube which picks up the pitot pressure communicates to this pickup tube. So we attach a U-tube manometer between these two ports, and that gives you delta P directly. Such pitot tubes or pitot-static tubes are used routinely in laboratory experiments. This is what a commercial pitot-static tube looks like. The pitot hole is right in front, and the static holes, a number of holes, are about 10 diameters behind the tip of the tube. It is assumed that within 10 diameters, the disturbance caused by the introduction of the tube will die out, and the pressure here, the static pressure here, would be the same as the static pressure if the tube was not inserted into the flow. This is an experimental setup where a pitot-static tube is being used to measure the velocity profile across the test section of a wind tunnel. Here, this is the pitot-static tube. Two holes, this is picking up the static pressure and this is picking up the pressure, the pitot pressure. These tubes are connected to a manometer which measures the pressure difference. By moving this tube up and down and left and right, we can investigate how the velocity of the flow changes across the section. A pitot rake consists of a number of pitot tubes attached with a supporting structure. Each of these pitot tube is connected to a tube, a flexible tube right here. And if there are 15 tubes here, there will be 15 tubes coming out here, each tube picking up the pitot pressure at the specific location. These are then connected to a multi-tube manometer where you can read the pressure difference, which is directly related to the velocity. There are various arrangements for these tubes. For example, this rake could be used to measure the velocity profile across a boundary layer. When we have a wall, a boundary layer develops on it, the boundary layer, the velocity changes very fast near the wall and rather slowly later on. So this rake allows us to pick up the velocity at very close points near the wall and points far away from the wall. This is an arrangement in which we measure the velocity of the flow in the wake of a streamlined body. We use a rake or pitot tubes in the wake of the body. The number of tubes come out here and are connected to the various tubes of manometer. These are manometer tubes which are connected to a reservoir type of manometer. The first picture is about a turbulent wake and the second picture is about a laminar wake. For measuring the airspeed of an aircraft, we need a pitot pressure, but we also need a static pressure, a pressure in the atmosphere which is not disturbed by the presence of the aircraft. It is a difficult proposition and various methods are used to pick up the static pressure. One of the more common methods is to have static holes on the nose or near the nose of the aircraft in the fuselage of the body. So these are a number of static holes. Experimentally, it is determined that the velocity of air past these holes is almost the same as the velocity of the free air, of the undisturbed air, which is equal to the velocity of the aircraft in still air. So these points pick up, or these holes pick up static pressure. The pitot pressure is picked up from the pitot tube shown earlier, and these two pressures are fed the static pressure into the body of an airspeed indicator, the pitot pressure into a capsule. Because of the difference of this pressure, the diaphragm moves, and as the diaphragm moves, through mechanical linkages, the needle on the face of the airspeed indicator move, giving us an indication of the airspeed. The face of the dial is calibrated to read directly the speed using the formula V is equal to twice delta P divided by rho naught. What is rho naught? Rho naught is the density of air at the mean sea level in standard atmosphere. Actually, the velocity should be under root twice delta P by rho, where rho is the density where the aircraft flies. But that would be very difficult to determine, if not impossible. So these dials are calibrated using density fixed as the density at the mean sea level in a standard atmosphere. And the speed measured in such a device is called the indicated airspeed rather than the airspeed. Indicated airspeed bears the relation with the true airspeed like this. When we fly at an altitude, the rho is less than rho naught, and so V true is more than the indicated airspeed. This gives you some idea of the airspeed, not the true speed. But fortunately, from the pilot's perspective, this indicated airspeed has more significance about the performance of the aircraft. And so, this is a very good indicator. The speed at which the aircraft stalls does not depend upon the true speed, but it depends upon the indicated airspeed. The optimized performance parameters are related to indicated airspeed. Therefore, indicated airspeed is truly what a pilot wants to know. Pitot-static tubes are generally very reliable as velocity pickups, but need to be used with care. The following are some considerations that are important. Theoretically, the pitot tubes must be aligned with the velocity vector. They should be pointing straight into the oncoming velocity. However, it is found that both the stagnation pressure as well as static pressure are not very sensitive to small deviations from the line of flow. So the error that you see in pitot pressure and the static pressure are seen here. You would notice yaw and pitch angle are the angle that the tube makes with the flow direction laterally as well as up and down. It is called pitch when the angle is up and down, and yaw when the angle is left to right. It should be noticed that the static pressure is a little more sensitive, but even for an angle up to plus minus 10 degrees, the stagnation pressure deviates from the true pressure difference by no more than 1%, and the static pressure difference varies by no more than 3%. That are quite small for many applications. This property of being sensitive to the flow direction is also utilized in determining the angle that the tube makes with the flow. In this, we use a tube with one pitot hole and 4 static holes, 2 in the vertical plane, 1 at the top, 1 at the bottom, and 2 in the horizontal plane, 1 in front and 1 at the back. And we read the difference in the pressure between these static holes. If the tube is pitched up, that is, if its nose is tilted upwards, then the pressure at the bottom static hole is more than the pressure at the top static hole. If the body of this tube is yawed in such a manner that the nose is out of the plane of the paper and the tail is tilted backwards, then the pressure at the hole behind the tube is more than pressure at the front. These pressure difference then can be calibrated to give you the angle at which the flow occurs in relation to the axis of the tube. This is the typical plot of the yaw angles and the pressure differences that we observe in the flow. Using this kind of graph, we can relate the angle that the tube makes with the flow. Another cause of error is because the static pressure reading is sensitive to the distance of the probe from a solid boundary. This happens because the probe and the boundary form a Venturi passage, a narrowing passage through which the flow accelerates, lowering the static pressure. Thus, if the tube is very close to the wall, then the flow here, as this area to flow in, underneath the tube it is this area, a reduced area. So the flow will need to accelerate. The recommended gap is at least 5 diameters. The tube should be at least 5 its diameter away from the wall for an error of less than 1%. It is safer to use a spacing of 10 tube diameters. But this error is largely in the static pressure measurement. The stagnation pressure indication is generally error-free, or there is little error in the stagnation pressure indication. Turbulence affects the pitot-static tube readings by varying the effective angle of the velocity vector. As the velocity components fluctuate, the net direction of the flow also fluctuates, and this could cause error in the reading. However, if the turbulence is isotropic, the readings are quite insensitive to the level of turbulence. And since the isotropic turbulence is the most common type of turbulence, this is not of much consequence. Another cause of error is the time constant of the pitot tube. As the pressure changes in the flow, the fluid through the tubes, the pitot-static tubes and the connected tubes need to move. So also the measuring fluid, the gauge fluid that we use for indicating the pressure needs to move up and down. It will take time for the fluid to accelerate and then come to rest. This limits how fast we can take the readings. Or if we can take the dynamic readings at all. The time constant of a pitot tube is the time it takes to acquire a constant value. It depends on the inertia and the viscosity of the fluid in the pressure lines. It also depends upon the length and diameter of the probe, the length and diameter of the tubes connecting the probe to the manometer, and the displacement volume of the manometer. The time constant is quite negligible for probes down to about 3 millimeter diameters. It is between 15 to 30 seconds. It really is not negligible. So you'll have to wait for about 15 to 30 seconds before you take the reading. But if the tube diameter changes or reduces further, the time constant increases rapidly. For the thinnest successful tubes of diameter 1/32 of an inch, a little less than a millimeter, the time constant is as high as 15 minutes. So one has to be very careful. It is not uncommon to use tubes of side 1/16 of an inch, about 1.5 millimeters in diameter. And so we have to wait for considerable time to take readings from such tubes. Such tubes also need very high maintenance, as they tend to clog easily because of the dust in the moving fluid. Orifice meter is another type of meter. It's an obstruction meter again, and it consists of a plate with a hole, with an orifice at the center. The tube has a diameter D, capital D, and the orifice has a diameter lowercase d. These are the recommendations for a design of orifice meter contained in ISO 5167. But an orifice meter of almost any design works, only that you'll have to worry about its calibration more. To analyze this orifice meter, let's look at the flow through such a device. There are two piezometric tubes connected, one ahead of the orifice plate and one slightly behind the orifice plate. The pressure or the water or the liquid rises up to this height in the first tube and up to this height in the second tube. As the flow comes out of the orifice, it first contracts, and as we have discussed earlier, it first decreases in the area and forms a vena contracta, the cross-sectional area where the diameter of the jet is minimum. There is a dead water region, a ring dead water region, just behind the orifice plate, and the liquid that comes out now slows down and fills up the tube completely. In an actual flow, the hydraulic grade line, which is the pressure plus the elevation variation of that, looks something like this. The energy grade line without obstruction is this. It is inclined towards the right because the total energy is decreasing slightly because of the losses in the open pipe. There is a pressure gradient in the pipe, as we have discussed, and because of that pressure gradient, the total energy is decreasing. So these are this difference measures the pipe losses because of the motion of the fluid in the pipe. But because of obstruction, there are further losses, and the energy grade line, the true energy grade line with obstruction, is like as shown. These are the obstruction losses. This then, the shaded area, then represents the velocity head. The velocity head in the beginning is the same as at the end. It is maximum at the location of the vena contracta. This flow is very difficult to analyze, so we make a model flow, a simplified model, and we assume there is no vena contracta. The fluid comes out as a jet of constant diameter. There are no losses. So the energy grade line till the second pipe is horizontal, and then it's because of the losses in the eddies that the energy decreases. There are no pipe losses. The hydraulic grade lines is quite a bit like this. The constant pressure in the upstream region, constant pressure at this portion, and then pressure increases as the fluid slows down. So we pick up these two pressures, pressure here and pressure there. Pressure at 1 and pressure at 2. And then these two pressures are related to the velocity in the pipe. How? First of all, by the mass balance equation, V1, the velocity at 1, times the capital D square, the diameter of the pipe, is equal to V2 times lowercase d square, the diameter of the orifice. This equation and the Bernoulli equation between these 2 points. It is easy to solve this equation, and with beta is equal to d by d, we get the velocity V2 as this. Velocity at the orifice. And the flow rate is V2 times A2, which is also V1 times A1, and we get this flow rate in terms of delta P, the density of the fluid rho, and beta, the diameter ratio, the diameter of the orifice to the diameter of the tube. The simplification introduced ignored many features of the real flow which caused deviation from the result. The viscous losses within the pipe that we neglected for the pipe length between port 1 to port 2, and ignoring these viscous losses inflates the volume flow rate. A loss in mechanical energy due to recirculating eddies. The exact location of the vena contracta is not known. The diameter of the flow at vena contracta is also not known. There are too many factors about which we are ignorant. And so we cover our ignorance by introducing coefficient CD. We multiply the theoretical Q dot, the volume flow rate obtained, by CD to get the true volume flow rate, and that CD is obtained by calibration before use. Typical values of CD are given in the chart. The CD value depends upon the Reynolds number and on the value of beta. As beta decreases, that is, as the orifice becomes narrower, the CD decreases, but the typical value is around 0.6. Not a very good value, and this tends to become constant if the Reynolds number increases beyond about 5 into 10 to the power 5. Another variation of an orifice meter which makes it much better is what is called a flow nozzle. Given here are the specification of an ISA 1932 nozzle. It just works on the same principle. Causes an obstruction in the flow which reduces the cross-sectional area and increasing the velocity. Application of Bernoulli equation would then give a decreased pressure, and we'll get the same equation for the volume flow rate as we got for an orifice meter. Q dot rho is CdA2 under the root twice delta P by rho divided by 1 minus beta raised to power 4. But in this case, because of the nozzle and the radius of the nozzle at the inlet, the flow goes in smoothly. There is no vena contracta formed. The jet comes out as a constant diameter jet. Of course, there are losses after that when the flow reattaches with the wall. So the discharge coefficient is now a much higher value. And the discharge coefficient you see is better than 0.93, about 1.5 times the discharge coefficient we got there, between 0.93 and 0.99. And about 5 into 10 to the power 6, it becomes constant at about 0.995. A very good discharge coefficient. And because of this, a flow nozzle is a preferred flow measurement device, except that it's more expensive to construct and more expensive to install. Another variation on the orifice meter and the flow nozzle is a Venturi-meter. Venturi-meter is nothing but a flow nozzle connected with a divergent section in which the divergence angle is less than 15%. So that the jet that comes out of the nozzle expands slowly and does not separate from the wall. So the recirculating eddies are not formed in that region. And because they are not formed in that region, there is very little pressure loss. So Venturi-meter is a very good device, except it is log, it is expensive, and it's difficult to install. It uses the same equation for the volume flow rate as we obtained for the earlier two devices, because it's the same mass balance and the same Bernoulli equation applied with the same parameters. The discharge coefficient is very good, of the same order as for a flow nozzle, in the Reynolds number range of 1.5 into 10 to the power 5 to 2 into 10 to the power 6. It is independent of the Reynolds number and can be approximated by CD is equal to 0.9858 minus 0.196 beta raised to the power 4.5. Since beta is less than 1, so the second term is really quite small and CD is very large. The beauty lies in the fact that for this Reynolds number range, CD is constant. So the volume flow rate is directly related to the pressure difference measured by this. The main advantage of a Venturi-meter over other devices is their much decreased head loss. The head loss coefficient for Venturi-meter is way below that of flow nozzles and the orifice plate. Another flow measuring device is what is known as a rotameter. It is very interesting. It's usually oriented, or it has to be oriented vertically as the flow takes place. This float is in equilibrium under two kinds of forces. One is the weight of the float downwards, and the other is the drag on the float because of the fluid motion. The drag changes with the velocity of the flow and with the location of the float within the diverging passage of the rotameter. When the float is down, the passage around is narrower and there is more drag. When this is for a given flow, for the same flow, when the float moves up, the passage around it is more, so drag reduces. For a given flow, the float adjusts its location such that it experiences drag equal to its own weight. We read the location of the float on the graduations on the transparent tube which carries the flow and is directly calibrated into volume flow rate. This is very commonly used in process industry. Another very accurate device for flow measurement is a hot fire anemometer. It is a very accurate device and has a very small time constant, so that the velocities fluctuating at high speeds in turbulent flows can be measured by it. It consists of a thin electrically heated filament. The heat loss from the wire by convection depends upon the flow velocity. If this rate of heating is lowered through the electrical circuit heating it, the flow velocities can readily be calculated. It is a device of choice for measuring the turbulence parameters. its time constant is small because the volume and the mass of the wire, the active element, is very small. So the temperature of this changes very quickly as the flow velocity changes. Another device is based on the Doppler principle. The Doppler principle states that the frequency of the waves traveling through the medium changes as the flow velocity changes. This is known as the Doppler effect. The shift in frequency is used to measure the velocity. We have a laser passing across the flow sections. The flow section is seeded with particles, very small in size, and the particles are assumed to move with the velocity of the flow. So the laser beam is reflected from those particles, and there is a frequency shift that occurs because of the velocity of the particles. So if we can electrically pick up the frequency shift, we can relate this to the velocity of the particles, which is related to the velocity of the flow, if the particle velocities are very small. Thank you very much.